Good morning, everybody. Welcome to the MPG Primer today. I have the absolute pleasure of introducing Sarah Urbut. She is a cardiology fellow at MGH and a postdoctoral associate at the Broad in the lab of Preeti Natarajan. She previously completed her MD PhD at the University of Chicago in statistical genetics. Her research focuses on developing statistical methods to handle genomic and clinical data. In her free time, she enjoys bicycling and Chicago pizza. In today's primer, she's going to present a practical primer on Bayesian statistics. So, here, Sarah.
Thank you. All right, I don't know. Okay, I don't really need a microphone. I'm pretty loud. All right, so hi, good morning, everybody. So this is a hefty title. Bayesian statistics is a very large field, and as appropriately, I have 84 slides just for the morning, which we are not going to get through. So it's kind of a choose your own adventure a little bit. And we'll start with the things that I was asked to talk. Actually, everybody, when they hear about Bayesian statistics, they say, well, what do you have against p-values? So I have a lot of things against p-values, but I'm convinced all of you to have things against p-values also. Not really, but so that's one of the topics that we can discuss. Then conjugate models, which are a really neat way of entering into Bayesian statistics because they combine sort of the uncomfortable part of Bayesian statistics is a lot of the sampling that we know about, MCMC, and you probably have heard of. It's a sort of painful but useful technique. And so we can avoid that with a lot of these conjugate models that are useful in mixture models, which is a later topic. And then, of course, if we have a little time, which we won't, we can talk a little bit about Bayesian clinical trials. Anyway. All right, so the p-value paradox. So what is a p-value is the question for the audience. Does anyone want to answer? Okay, we don't have to. That's okay. It's early. Right. So it's a probability of seeing a statistic as or more extreme, given that the null is true. It doesn't say anything about the alternative. And also, quite often, we're not actually interested in, we don't want to know the probability of seeing a statistic as or more extreme, given that the null is true. We want to know that the probability that the null is true or the probability of the alternative is true. And so to illustrate this, I kind of came up with this neat diagram. This is Dennis Lindley talks about how a p-value really isn't evidence for the alternative at all. And so this is two different distributions. So the distribution on the red is the null. The distribution on the blue is the alternative. Also, just to note, all of these slides had a lot of fun, pain. This is a software. It's called Quarto. You probably have heard of. So Quarto has a way of making presentations. And the nice thing about this is afterwards you can log on and go through all of the code if you want to try to figure out how to make these simulations yourself, which I highly recommend. I mean, not, but I just think it's a great way to learn statistics to go through the code. So anyway, all right. So in this diagram, we have statistics that arose from a null distribution, and we have statistics that arose from an alternative distribution, right? These are the two truths situations. And you can see that if I observe a value which yielded a p-value of 0.05, this 2.5, under the null distribution, the posterior probability, which is the probability, or the likelihood, the probability of seeing that statistic given that the null is true, is actually higher than the probability of seeing that statistic given that the alternative is true. So we always need to consider the evidence for the alternative when we're evaluating the null. Right. And this is what I was describing before, is that the statistic that a p-value gives us, which is the probability of seeing statistic as or more extreme given that the null is true, is not really what we're all trying to get at as scientists, which is the probability of a hypothesis given the data. So, and this is not actually restricted. This sort of philosophy, the idea of this prior that a lot of people think about with Bayesians, it's not completely, you can have sort of an ambivalent prior, what we call a frat prior, and you can come up with the same sort of drawing that a frequentist would, but it gives you an entirely different interpretation about the probability of a hypothesis given the data. And I'm going to show you this. So these are some pearls in the Bayesian framework. The parameters are random variables. We can actually get uncertainty because we get this distribution over what we think the hypothesis is, the null hypothesis or the alternative hypothesis. We can integrate evidence from outside sources using our prior distributions. And also we get this natural quantification of uncertainty through either sampling or through the conjugate distribution because we get a distribution on the hypothesis. Okay, so here's a classic, this is what our posterior distribution of a hypothesis is. So our probability of the hypothesis given the data. And we observe this point estimate. This is how we draw this. So a credible interval and a confidence interval. What I want you to see is that they're actually quite similar, right? They overlap because I used a very flat prior. But the interpretation of them is really different. So what is a credible interval? And what is a confidence interval? Probably start with the confidence interval. What is a confidence interval? Does anybody? Okay, so it's the long, yeah, it's okay. Who's running? All right, so it's the long run frequency of observing a statistic within this window. So that would say if I ran, and I say who's running, because it's kind of like who's running? Who's doing this many experiments, right? Time is short. We got to move. Okay, so if I did 1,000 experiments, 95% of them would contain the true parameter of interest because the parameter is considered as fixed in the frequentist analysis 95% of the time. That's kind of a long-winded way of describing it, right? What does that mean? If I ran this experiment 1,000 times, if I created 1,000 times that I would actually have the ability to run the experiment, the true parameter of interest would be in this interval 95% of the time? I don't know. That's a lot of words. So a credible interval, which as you can see, considers sort of the same area, is the very intuitive explanation. It's just saying there's a 95% certainty that the random variable lies within this interval, that it actually lies within this interval. And that's because basically the probability mass under this distribution lies in that area. So you construct this new distribution based on the posterior distribution. It has a mean and a standard error in this case, or a mean and a variance in this case. And you say, what is the interval that would contain 95% of the mass there? Much more interpretable. Okay, so now we're getting to Bayes' theorem, which is, I think a lot of us have seen this in introductory math statistics. It's the probability of the hypothesis given the data times the probability of the data given the hypothesis times the probability of the hypothesis. So you can forget the constant in the bottom. And the probability of the data given the hypothesis is called the likelihood. And that's what a frequentist deals with. And the probability of the hypothesis is called the prior. And that's what people think of Bayesian statistics is limited to. But it's really not. It's this compilation of these three elements, actually. This normalizing constant is kind of annoying, but it's there, that really summarize an entire body of statistics from the Reverend Thomas Bayes. And it's quite useful. Okay. And so this is an example. You can go through the code, actually. But as I'll talk about these, you'll see that things sort of repeat themselves or also foreshadow themselves. That's kind of intentional. It's good to repeat these things. But this is a nice example of a Bayesian, how the Bayesian framework works, right? So we have some prior belief about what we think the allele frequency is. This distribution is called a beta distribution. That's not important. That's just a word. But basically, it's a distribution of how confident we are in the value of the allele frequency. Right, it's a random variable. It's fluctuating somewhere around there. It's not totally random. Somewhere there's a true universe that suggests what the actual allele frequency is, but it serves as a random variable in this sense. So there's this prior distribution. Then we meet our new observed allele frequencies that has this distribution that's the green, right? And then so it's some sort of amalgamation of the prior and the likelihood gives us our posterior. And as I'm going to talk about in the conjugate section, there's some really nice properties that I actually don't have to do any sort of sophisticated sampling. The way that when you work out the algebra, effectively I'm just taking each of these new observed units, combining them with the prior, and then I get this really nice convenient result that gives me a posterior without having to do any sort of fancy calculus. Not that fancy calculus is wrong, but okay. So let's go back to our p-value friend. So our p-value, as we said, was more in the likelihood camp. It's not the probability of the hypothesis given the data, it's the probability of the data given the hypothesis. And Bayesians have an answer for this as well, but remember we wanted to talk about the alternative. That's really important. So we come up with this idea of a Bayes factor. And there's, to be confusing, two kinds of Bayes factors. One evaluates the probability of the data under the alternative hypothesis divided by the probability of the data under the null. And that's called beta 1, 0, because 1 is in the numerator and 0 is in the basement. Or there's the alternative, the Bayes factor 0, 1, which is the probability of the data under the null hypothesis divided by the data under the alternative. The equivalent statements just inverses of one another, but they do it to keep you like a bar for entering. So you got to have a license to become a patient. Okay, so why is this important? Well, I'm going to show you that it's important. So I wear several hats, none well, but in one of them, I spent some time in the hospital, right? And it's very useful because you can quickly take some feeling about your prior belief combined with this nice convenient way of parameterizing our evidence under two different hypotheses and generate a posterior distribution really quickly. I'm going to show you that magic. So you can use that. Okay, but first, right. So what does it actually mean when we observe these very low p-values? So I made this nice app, actually. See if we can actually access this. I'm a little scared because if I access this, we may never get back. I don't know. Do I do it?
Do it.
Okay, we're going to do it. Or not. We may not do it. Okay, that's not working. Oh, do I have to? Huh. Great. Well, that worked well. Oh, because I'm only sharing one. Okay, great. All right, sorry, guys. Interlude. Okay. So this is really nice. Okay, so this is a shiny app. So we have this prior belief on what we believe about the truth of the association, right? So that falls into our prior. That's about the hypothesis. Being associated or not being associated is the hypothesis. So you have that belief. Now, we observe this p-value, which translates, as I was describing, this Bayes factor. The p-value is in the likelihood camp. So the p-value itself is not directly the likelihood, but it's in that camp. It's the probability of seeing a statistic as a more extreme, given that the null is true. And say that p-value suggests that there's a 99% probability of seeing the data, given that, well, it's a probability of 0.01% of seeing the data, given that the null is true. But it doesn't mean a 99% chance of true association. That's the key point in this plot. So, but if we combine that, so if we convert that p-value to a Bayes factor and combine it with the prior, we actually get only an 18% probability of the alternative hypothesis given the data. And we can try this with different assumptions, right? So in this, so we can try actually a larger observed p-value. And of course, that's going to make our posterior even lower. And we could also try the prior probability of association could increase this actually, right? So that's going to increase our posterior. So there's definitely fluctuations here. But the key point I want to make here, and if you walk away with nothing, is a p-value of 0.01% does not mean that there's a 99.99% probability that the alternative is true. It actually tells you nothing about the alternative. It just says that that's quite unlikely under the null. But it depends. I mean, I could say, I see 3 tusks, so it's probably not an elephant. That's probably true, but that doesn't mean it's a person, right? Like it's, yeah. So anyway, go back. Okay, now it's all gonna fall apart. Whoops, now we stop sharing. Sorry about that, guys. Okay. Oops. Look at that. Okay. All right. So we have this convenient way of converting p-values to Bayes factors, as I was describing, to translate this frequentist quantity in something that's useful as Bayesian, or useful, just period, and full stop. Okay. And so there's these 3 brilliant guys who came up with this paper in the 70s, actually, that translated these p-values to a Bayes factor. And this, remember I said I was going to be very confusing and throw around Bayes factor 0,1 to Bayes factor 1,0. So now we're talking about the 0,1, just to make it interesting, right? And so what does the Bayes factor minimum is? Well, it basically says this is the minimum amount of evidence for the null hypothesis we would get making the most sort of optimistic assumptions about the alternative hypothesis. Because if this Bayes factor is weighing the probability of the data under the null hypothesis over the probability of the data under the alternative hypothesis, then if we had really big basement or really small, attic, then we're effectively going to get a very low Bayes factor minimum. And so that's saying a p-value of 0.05 translates to this minimum Bayes factor, p-value of 0.001 translates to that. Well, what does that mean? That basically means roughly that there's 0.37 as much evidence for the null as there is for the alternative, which is actually only 2.7 times as much evidence for the alternative versus the null. That's really not convincing at all. Like, I'm not making any decisions with that. And yet we build a lot of our decisions and certainly in medicine or in science based on this p-value. So you have to be really thoughtful. Now, there are situations in which observing that p-value, depending on the population of other tests or on our prior belief going in here, like I just showed in the app, might actually be very convincing. And so it's useful to think about. And often I would argue, we actually are all Bayesians as scientists or as clinicians, because we probably wouldn't run an experiment unless we had some prior belief that we thought there might be a reasonable chance of it being workable or true. But that just de novo, without any information, with using effectively a flat prior, ignoring the prior information, and just evaluating the evidence for the null versus the alternative, that's the translation. That's pretty powerful, actually, if you think about it. Like, how does that make us all feel? Should we do a check-in? No. Okay. All right. We're moving on. Jokes are not hitting this morning. Okay. All right. So, so now we can flip that around and take the denominator over the numerator, right? And the evidence for the alternative versus the evidence for the null. And effectively, this is a table also from that Selke, a follow-up Selke paper. And they actually said a Bayes factor of 1 to 3 is barely worth mentioning. So that 0.05 taken in and of itself is between 1 and 3. It's a Bayes factor of 2.7. We're not even going to talk about it. I mean, that's kind of sad, actually. I don't know. Okay, so all right, so how do we turn this Bayes factor into something that can give us those posterior probabilities that we're interested in? Well, remember that the example that the sort of cardinal important rule that we learned in from the beginning slides, that the probability, the posterior probability, the probability of the hypothesis given the data can be written in this way. And you can actually rearrange the algebra and take that likelihood, the probability of the data given the hypothesis times the probability of the hypothesis, as basically a ratio of the Bayes factor times the prior odds. I'll show you this. Right. So we can take the Bayes factor 1.0 times the prior odds. Now this is in the reverse way, the probability of the data given the alternative over the probability of the data given the null, and then times the prior probability of the alternative over the prior probability of the null. And you can quickly translate this wherever you are, you just in the sort of the back of your mind, if you think that de novo, the alternative hypothesis is 3 times as likely as the null, and you observe this Bayes factor that perhaps corroborates or goes against that feeling, and you can convert that actually into a posterior odds, which can be converted into a posterior probability. And so these are the important takeaways from this, right? So p-values are answering very different questions that I think that we're most thinking about, and that we maybe de novo think that they should be answering. A Bayes factor allows us to compare these competing hypotheses in the likelihood space, which is still in the Bayesian space. And even these significant p-values provide weaker evidence than typically assumed. And actually, what's nice is, and it's one of the slides that I've commented out because I didn't know if I'd have time, but if you, so if you actually draw the log 10 p-value versus the log 10 Bayes factor, the evidence, the translation is it's actually upshifted effectively, meaning that the minimum Bayes factor is always actually less evidence against the, well, it's less evidence against the alternative, less evidence against the null than the p-value would suggest. And so, right, these Bayes factors have a natural interpretation, and you can conveniently convert when you have the Bayes factor, when you have the prior probability into posterior probability. All right, so multiple testing. So we're moving on. We're making good progress. So now we've developed these p-values, and we have not just 1 or 2 p-values, but we have many p-values. Many people in this building have many p-values, right? That's kind of our idea. And so there are some sort of cardinal feelings about how we deal with all of these hypothesis tests. Because if we're running a lot of hypothesis tests, even in a frequentist sense, we realize that we need to control the probability of seeing the data, given that the null is true, is very small. The probability of the complement of that taken to a large number actually gives you a value that's not so small. And so what do we do with this information? Right. And so this is where I was going to draw some sort of the way that we typically think about this in a frequentist setting. And this is actually how I sort of started out when I was an undergrad. I was introduced the idea of false discovery rates. And I said, that's pretty cool. It's important to think about. But how do you calculate some of the important quantities there? So, all right. So this is our null. And this is our alternative. Now, you guys may have seen this, but suppose that we observe a statistic that's right here. Okay, this is our Z. And we observe not just that statistic, but we observe a whole list of statistics. We have a whole list of findings that we're calling significant. That often happens in genomic discovery, right? So we have this list that we're calling significant, and we want to know, instead of the probability of the data given that the null is true, what we said the p-value was, we want to know the probability that the null is true, given that we're seeing a statistic as or more extreme. We want to invert that. And that's called a false discovery rate, which is typically thought of as a frequentist quantity, but I'm going to dispel that notion today. Oh no, what did I do? Okay, oh my goodness, okay, all right, so this is called FDR. All right, so we observe this statistic, and essentially we're looking at the ratio, and we're saying that this is the portion of the statistics as or more extreme, given that the null is true, because this was the null distribution, right? And this is the whole list of discoveries. So the fraction of this, we'll call this A, over this area, B. So A over, well, we could say that perhaps this is B, this is the portion that's coming from the alternative distribution. So A over A plus B equals FDR. But the interesting thing about this is we actually don't know how close these distributions are. And we don't know the enrichment of our set of tests in alternative distributions or alternatively enriched in null distributions. So that's where we have this nice result. And if you essentially plotted a histogram of p-values that were all generated from a null distribution, they would be completely uniform. So you look at where that distribution forms a uniform height divided by 1, basically normalized when it's density. And so in this sense, we see the pi is 0.7. So the proportion of null tests is 0.7. That means it begins to form the null distribution. 70% of the tests effectively are forming that null distribution. And so that value is equivalent to our prior. So now if we're turning this into a Bayesian quantity, the probability of the null hypothesis given the data is proportional to the probability of the data given the null hypothesis times the probability of the null hypothesis. And I can write this as pi 0. And then this probability of the data given the null hypothesis, we know is our likelihood, right? So we can calculate that. Okay, so the challenge though is how do we calculate pi 0? And also perhaps we're not interested in an entire list of tests because we're only observing one test at a time. And so that's where I'm going to introduce you to this local false discovery rate that was pioneered by, well, Matthew Stevens, my PhD advisor, but is I mean it probably has been around before, but it's very useful to think about in this sense, and it's inherently it can be inherently a Bayesian quantity. Okay, so this is what I was just describing. So the probability of the null hypothesis given a particular z statistic is the probability of the z statistic given that the null is true times the probability of the null hypothesis, right? Which is just 1 minus the alternative hypothesis there. Okay, and so in this parameterization, we have the density function, which is the probability of the z statistic or the data given that the null is true. And this is for null statistics, right? Is a normal function. So it's a normal density, 0 sigma squared. Now, what if it's from the alternative distribution? What if we meet a z statistic from the alternative distribution? Well, in that sense, we're actually going to have, this is where, yeah. So, okay, so we have an overall distribution that, I'd probably put this order in funny, but basically we have, let me draw this out differently. I think I have this one. Okay, we're going to have a bit of a tree. And so in our first tree, before we meet any data, we just have the probability of the z statistic, where it lives, right? And so that's going to be normal, 0, sigma squared. This is called, or prior mean, prior variance. And this is of the true effects. So these are the true effects are centered around some distribution where perhaps the prior mean is 0, but some of them are true. And so they're out here. This is the true effect. Now we observe a new one that's noisy, and that's going to be centered around that true prior effect plus some noise. And then our posterior, which is going to be the probability of the z given the z hat, is now going to have its new posterior mean and this new posterior variance. And that's calculated by effectively integrating over the prior mean and the likelihood, the observed data. And now you get this marginal likelihood, which is the probability of seeing, so the marginal likelihood is now going to have, when you integrate this observed z over the prior mean, it's going to have this noisy mean and the prior variance. Okay. So what did I show here? Right, yeah, this was the prior likelihood. Okay, so, and the overall distribution then, when we observe, it's a mixture, right? It's a mixture of these null statistics and these alternative statistics. And this was sort of the formula. So the posterior, the distribution of statistics is basically, the prior is a mixture over each of the component distributions, and this is the conditional likelihood. So the point I wanted to make here was, sorry, there's too much for this. Oh my gosh. Sorry about this. Okay, so the point I wanted to make here, though, was that figuring out this balance, the distribution, the pi1 or the pi0. Figuring out the balance that sort of optimizes the likelihood, the observed data, is tricky. And it requires these empirical Bayes techniques that really determine what sort of optimizes. You can, in empirical Bayes, you're optimizing the likelihood. So finding the balance of pi's that really optimizes seeing the set of statistics you have. So perhaps you have a lot of really large effects that aren't noisy. So then your pi0 is very small, your pi1 is quite big. Or perhaps you have a lot of small noisy effects, and then your pi0 is going to be very large, and your pi1 is going to be very small. And similarly, the balance of sigmas tells you exactly how large the effects are. And so you can fix one and try to estimate the others, or you can try to fix them and estimate them jointly in a Bayesian sense. Okay, so this is the population. So what we observe is we observe these effect sizes. We of course don't know which ones are null and which ones are true, right? So, but the goal is to try to estimate that. And let's see, I have this nice, right? So after you've done that, you can see that when you apply this technique that's effectively shrinking effects with noisy standard errors that are quite small towards zero, you get a plot like this. And how does it learn? How does it learn that nicely? So effectively, it's a mixture. Remember, as I was describing, it's a mixture over these prior variances. And so for each statistic that you observe, you say, well, is it more likely to observe it with a large prior variance, which is a true effect variance, or is it more likely to observe it with a small prior variance because it's so noisy? And so the larger prior variance that you get that really makes sense with the data that you're observing tends to shrink the data less and sort of shrink basically the prior, which is a spike prior, it's fit at zero, will matter less, and the data matters more. And so then in that plot that we just had, you'll tend to see that large effects are boosted and small effects are shrunk. So you can see that. Yeah. Okay. So what is MASH? So MASH is really an extension of this. But now, instead of looking at only the population within a univariate population, so in one trait, we think about the abundance of large and small effects. So that's the proportion, that's the pi, and then we think about the scale of the effects. Now we have multiple effects in multiple traits. And we might say that the effects in other traits tend to boost the effects in one trait. And so that U matrix is now actually capturing the shape or the relationship among traits, but it's also got the scaling parameter that's just like this, just like the prior variance that we observed there. So the take-home point is the prior variance actually helps you boost the data that you're observing. And if we have a large observed effect with a small noise, then we're actually going to boost the posterior and recognize that a large prior variance would sort of best fit that situation. And if we also observe that there are large effects in other conditions, we'll boost it even more. Right. Okay. So this is kind of a neat. So the way to wrap your head around this. So as I said, this sigma 1 and sigma 2 are the prior variances. What are the terms on the off diagonal? So those are the covariance scaled by some correlation. And so the correlation really controls. So if we have two traits, I think I have this plot here somewhere. Right. Okay. Well, if we have two traits, so trait 1, 2, and they're correlated, but it's quite noisy, right? So we'll see a big cloud of points. But if one increases in the same scale that the other increases, then it'll be the straight line. And so the question is, well, how would you get something that's on the off diagonal, right? So that you would just change the relationship between the prior variance for 2 and the prior variance for 1. So suppose that 2 is always constituently higher than 1. So you get something like this. And if 1 is always larger than 2, you get something like this. And the row controls how cloudy those are around each other. And that prior assumption, if it's congruent with what we're observing, right, then we'll tend to sort of boost that component of the mixture model. And the ultimate posterior will be heavily informed by that component of the mixture model. Okay, so how would I get a 1-1 line? So that's sort of an exercise to go through yourself, but that effectively is saying that the correlation coefficient is 1. They're perfectly correlated. And this is not a 1-1 because I was trying to show a situation in which the effect in 2 is greater than 1. So that prior variance for 2 is greater than 1. But if you wanted a 1-1 line, it would just be, this whole matrix would be 1s effectively. Okay, so bringing it home, bringing it all together. Different shrinkage approaches that we have. So if we have these observed effects, they're quite noisy. In a univariate shrinkage approach, we treat each group separately. We don't consider how the effect tends to behave in other conditions. And if we have, large effects, they're tend to be captured by components of the mixture that have a large prior true effect variance. So we'll shrink the prior, shrink the shrinkage, if you will, and recognize the data. And if we have a small noisy effect, we'll tend to sort of augment this prior, which has a spike at 0, and exclude the data. And if we have multivariate shrinkage, the relationship isn't 1-to-1, because we might observe 2 small effects, but in one small effect case, the effect in other conditions was quite large. And in the other small effect case, the effect in other conditions was small. So in the first example, we tend to boost it because we recognize it had friends. And the friends were all going to the party, and so it wanted to sort of increase as well. And in the second case, we'd recognize it seemed to be sort of noisy across the board, so we'd shut that down. All right, so observed effects are noisy, only considering information in ones, yes, and sharing is caring. So I can't believe how quickly we're going. So ask questions, please. No questions. Okay, all right, well. Yes, please. Yeah.
Alternative hypotheses. So how do you do multiple alternative hypotheses? Do you just compare them?
Right, yeah. So you would do, so in the first step, good question. So in the first step, you would have multiple Bayes factors, right? Because you would be weighing the evidence of the null versus the alternative in multiple situations. And then you would develop a posterior probability for each one. But presumably, so you could think about having, this is a cool situation. So you could have a matrix, basically, that quantified the prior effect, the prior variance, how strongly you believed or didn't believe each one of those prior hypotheses. So that would be incorporated in your prior. And then your likelihood, instead of being a univariate likelihood, so a univariate Bayes factor, because a Bayes factor is really this ratio of normal densities, right? So in a one situation, one hypothesis testing situation, you have the probability of the data, suppose it's normal, under the null hypothesis over the probability of the data under alternative 1. Now, if you have that in multiple conditions, you have a vector, which has a multivariate normal distribution. Presumably, there's some correlation or covariance between the two. Perhaps there isn't. I don't know. So if you had that, then you could actually use a MASH type situation for that question, because now you have your observed likelihood as in across multiple features, as well as the covariance matrix for that. Yeah. Yeah, that's a really good question. Roman, yep.
Wait, so the people online could hear.
This is great, Sarah. Question for you around, do Bayesian statistics ever hold back novel discoveries, in that if we are too attached to a prior, it's difficult to violate our expectations?
Ooh.
For instance, like what I'm thinking about is like really unexpected discoveries. Like, recently there's been implications that MS are maybe due to varicella zoster virus, and
Yeah.
like we had no idea about that. So how do you deal with
Right.
something like that?
Yeah. So great question. Okay. So carefully is the first answer, right? So okay. So I have this plot actually. I quite like, because Bayes actually has this built-in safety valve, a built-in sort of what you call steering wheel bag. What am I thinking of? Yeah. Airbag. That's the word I'm looking for. I ride a bike, not a car, as you can see. Yeah, carefully also. But okay. So in this situation, I'm cutting to the chase a little bit, but there's these conjugate priors, which are these convenient parameterizations, right? But this is a neat example. So okay, so there's 3 different priors here. So I have this flat prior, which is completely indifferent. I have no idea. I'm going in and I'm saying I have no idea if it's big or small. I have an informative prior, which is helpful because it's bringing me towards the truth. And I have not only an uninformative prior, but it's actually incorrect. So uninformative would be totally flat. Incorrect would be wrong, right? We all know the meaning of that. And what's the okay? And what the neat thing about this is, you're straying from the truth, but you're not straying that far from the truth, because we are combining evidence from. We are combining the likelihood. But you are moving it a little bit away from the truth. That's for sure. But I think my answer to that would be, in the long run, so I'm being a frequentist now, I guess, isn't in the long run, we're running, isn't imparting no truth all of the time. So having a flat prior effectively, and not incorporating anything that motivated our very expensive experiment, isn't that more of a danger than some of the time moving yourself towards the truth and some of the time moving yourselves away? That's like a philosophical question. We need like a different discussion for that. But so there is a danger, certainly, of if you have too punitive of a prior, certainly sobering your expectations too much. And there's also a danger in the other way of, if you have too informative of a prior that moves you towards an optimistic direction or the wrong direction. That's also a concern. I think in practice, because there's like, a concern, there's an inherent sort of animosity towards overzealous priors. I think in general, we tend to use flat priors, at least in the literature I've seen, certainly in medicine. But the other, and maybe this is kind of from the clinical trial standpoint, is, as I showed in the beginning, the beauty of Bayesian statistics is that even with a flat prior, you get the same shape distribution as the frequentist analysis. The confidence intervals and the credible intervals have the same numeric values. But the conclusions that you make, the philosophical conclusion that you make, which is I have a 95% certainty about the value of the parameter, is very different than this sort of long-winded, hand-wavy, in the long run frequency, the constructed interval will contain the true parameter of interest 95% of the time. Like, what does that mean? How is that helping me make decisions in the clinic for 15 minutes? I can't even say that sentence in 15. Well, I can because I talk too fast, but often people can't, So, yeah, so that's my soapbox. Okay, all right, we're moving on. So what do I want to talk about? So I want to talk about conjugate priors. I think that there's a lot of, I've been thinking about this talk a lot, and science is tough right now. It's kind of makes us ask a lot of questions, but I think at its basis, science, math, these things are beautiful, and we got into this because they are beautiful. And so I think it's important to recognize that sometimes. Conjugate priors are beautiful. And they're beautiful because they save you a lot of work, frankly. So all the calculus that I was showing here, basically this integrating, you can imagine that, that nice integral that we remember, which is integrating the likelihood over all the possible values of the prior, can be saved because we have these convenient parameterizations. So a very, very simple that we use in genetics a lot is the beta distribution. So it's a probability over probabilities. Basically, it's a distribution over, we could say, allele frequencies, for instance. So we have some prior belief of what that is. And the relationship here is these are called hyperparameters or parameters of the prior. So alpha and beta roughly capture something about, you'll learn in statistics that everything sort of has a shape and a scale, roughly, basically. So the relationship of A over A plus B gives you the mean, basically. And A plus B, the sum, tells you how concentrated that is. It's like the precision or the inverse variance. So if you have a really high A plus B, it's going to be really confident about your mean. And if you have sort of a very flat one, it's like in the MASH example, you're really uncertain about that spike. Okay. All right. So then we observe so many successes and so many failures. Perhaps that's allele counts, perhaps it's coin tosses, et cetera. And what's beautiful is instead of having to do that complicated calculus, we just add the successes to alpha and we add the failures to beta, or however you want to parameterize it. Okay, and so this is what I was trying to show earlier, is basically under the flat, the informative or the uninformative wrong prior, you actually approximate a posterior that's kind of robust to these poor assumptions, because the more data that you observe, the less the prior matters. And that's actually really evident. I love the beta distribution for this example, because every time you can see actually that you update this posterior distribution, yesterday's posterior becomes today's prior. You update your distribution, and that alpha, which has, or the beta distribution of 2, 8, which is alpha 2 and beta 0, 8, matters less and less. After we observe the third group, we've kind of totally moved around. So that sort of answers your question. I think that we have this robust safety valve or airbag that helps us respond to new data that we observe. Okay, anyway, so that's a nice result. Okay, and so this is showing sort of after one observation, so our prior distribution is all the way over in the red. And after 10 observations, we've essentially moved away quite a bit. So there's that nice convenient. All right, so then there's another example if we have multiple alleles. And a Dirichlet is important. It's kind of a natural extension. The beta is like a simple case of Dirichlet. But I'm throwing that out there because if we get to the mixture models, we can discuss that there. But effectively, so now I have a vector. Instead of just having one probability, I have a vector of probabilities. And they have this prior distribution called a Dirichlet. I'll show you the nice plot here. Okay. So basically, suppose that I have, it lives in this space, right? So suppose there's the probability of 3 groups, and they live somewhere in the space where they sort of all add to 1. And what's nice is, as I was describing with the beta, if the value is large, the probability mass is concentrated more in the center, even if it's 1, 1, 1, or even if they're equivalent, even if this triangle looks more like this. If it's a triangle, it's concentrated in the center. And if we're really uncertain, it's quite a big cloud of points. All right, so let's go back. So now we have this prior of 2, 2, 2, which means it's basically the triangle. Everything is evenly distributed, but it's a little bit more concentrated than a 1, 1, 1. And we observe these 10 A's, these 5 B's, and these 3 C's. So we simply, our likelihood is a multinomial likelihood, the probability of observing 10 given a particular value of the parameters. And then we just add those values, the likelihood values, effectively the new counts, to the prior distribution. And we get this beautiful cloud, which is quite simple. There was no calculus required, no pain, just get new clouds. Anyway, so that's the Dirichlet there. Okay, and then one final, the conjugate normal, and this is important because that is actually, we take a lot of advantage of that in ASH and MASH. And so we have this prior distribution. So the prior true effect, mu or beta, right? And if you look at the ASH or MASH literature, it's centered around some prior mean and some prior variance. And I like to think about this because this is the true effect variance. This is where the true mu or the true beta live. There's some distribution of 0, truly 0, and some distribution that's not truly 0, right? It lives on that line. Now, we observe a new statistic, a new beta hat, we will, it's noisy, and it's centered around that previous truth plus some variance, some noise. And you could write it out basically as a linear combination. You could say that z hat is equal to z plus, well, I shouldn't have used that. Okay, let's do it this way. Sorry, guys. All right, so we could say that b hat is equal to b plus z, where z is normal 0, 1, and this is considered sort of an error. So in the exchangeables, oh my goodness, what did I do here? Okay, keep doing that, don't I? Yeah, all right, okay, so we assume it's known. We assume that the noise is known. So now the question is, what do we get the posterior? And so we're going to do some fancy math, some fancy rearrangements of terms. It's not that complicated, but there's symmetry here. So if you notice, this is the likelihood one on, I guess, on the right, is x minus mu. You know the normal density. And then on the left, it's the expression for the prior, which is the prior minus the observed prior that we're evaluating at a particular time minus its prior mean. So when you rearrange those terms, you actually get this beautiful expression for the posterior, which looks just like the first one, right? It's a posterior mean, so it's a normal distribution. So it's got, instead of being centered around the prior mean, now that it's seen the data, it's centered around the posterior mean and the posterior variance. And a neat thing about this is, so this is going to be the posterior mean, and this is going to be the posterior precision, if you will. So you can actually think of that. This is, again, Bayes is beautiful. We can think of the posterior mean as a weighted average, basically, of the prior mean, how much we believe the prior distribution, and the likelihood. And how do we get those weights? Well, it's effectively proportional to the data precision and the total precision, right? So if we actually have strong confidence in the data, and we're very flat prior, like we were talking about in the ASH example, where we had a very flat prior because we had these large sigmas, right? And the data is strong, then we would actually move more towards the data. And if we had a very large data variance, it was very noisy or very imprecise data, precision and variance are inversely proportional, then we would actually move more towards the prior. And so smaller values of the prior variance would support it. And that's pretty cool. So our posterior mean is a direct combination of how strongly we believe the data likelihood and how strongly we have a prior belief. And so the more evidence we have from our observed data, and perhaps the flatter the prior, we will get closer. Our posterior mean will look more like our data. And let's see, do I have any plots there? Yeah. I guess I don't have any plots, but that effectively would give you a distribution like I showed for the beta plot, where you'd have your prior mean centered around 0. You observe your data looks something like this with it's very narrow, so it's very precise and it's large. And then your posterior mean would probably be somewhere around here. Okay, great. Okay, and then so this is just showing, and we take advantage of this in these summary statistics. So instead of having to deal with all of the observed values, we actually, in a GWAS, we get a summary statistic, right? That's often what we work with. We get a summary statistic. So you have this beta hat in its standard error. And it turns out you can conveniently use the conjugate formulations for that same. Okay, great. Yeah. So let's see, I just want to make sure there wasn't anything I wanted to say here that. Let's see. Okay. I don't think so. Yeah. 4 minutes? I have 4 minutes. Okay, well, that's a good, yeah. So, right. So when we don't have, okay, this empirical base. So one of the questions is, how do we estimate these, right? How do we estimate the sigma and the pi, for instance, from the data? And so actually we can use techniques. So in the next section, I have this thing called the EM algorithm. So you sort of fix one and then estimate some of the other priors, the pi hat, for instance, or you can sort of choose sigma values, the scales for the that we were using in the variety of the grid for ASH or MASH from the data. So a set of sigmas that we think are very small or very large that would sort of fit it appropriately. Or sometimes these hyperparameters, like I was talking about in the beta distribution, we might have some belief from the data, some empirical data that suggests that we should use this and actually saves us a lot of time. Because when we can't use a conjugate parameterization and we have to do MCMC sampling, that takes a lot more time. So if we have a empirical estimate of what we think the alpha and beta are from the overall data, we can plug those in and make our life a lot easier. That's often done for the hyperparameters. Okay, so right. So the next part of the talk was on mixture models, and I have some really nice didactics and things inside. So I don't want to like rush through it. So either I can come back or you guys can go through it on the slides online or email me. I'm happy to set up a time and all these things. I'm really passionate about this stuff. So thank you guys so much for listening, for your great questions.
Thanks, everybody. Remember, we have 2 weeks off, and yeah, have a great day.